So, suppose that there's a happy bug in the center of a circular water puddle. The bug is periodically shaking its legs in order to produce disturbances that travel through the water. If these disturbances originate at a point, then they would travel outward from that point in all directions. Since each disturbance is traveling in the same medium, which is water, they would all travel in every direction at the same speed. The pattern produced by the bug's shaking would be a series of concentric circles as shown in the diagram. These circles would reach the edges of the water puddle at the same frequency. An observer at point A, the left edge of the puddle, would observe the disturbances to strike the puddle's edge at the same frequency that would be observed by an observer at point B, at the right edge of the puddle. In fact, the frequency at which disturbances reach the edge of the puddle would be the same as the frequency at which the bug produces the disturbances. If the bug produces disturbances at a frequency of 2 per second, then each observer would observe them approaching at a frequency of 2 per second. Now, suppose that our bug is moving to the right across the puddle of water and producing disturbances at the same frequency of 2 disturbances per second. Since the bug is moving towards the right, each consecutive disturbance originates from a position that's closer to observer B and further from observer A. Subsequently, each consecutive disturbance has a shorter distance to travel before reaching observer B. Therefore, it takes less time for the sound to reach observer B. Thus, observer B observes that the frequency of arrival of the disturbances is higher than the frequency at which disturbances are produced. On the other hand, each consecutive disturbance has a further distance to travel before reaching observer A. For this reason, observer A observes a frequency of arrival that is less than the frequency at which the disturbances are produced. Therefore, the pitch is lower than compared to observer B. The net effect of the motion of the bug, or the source of the waves, is that the observer towards whom the bug is moving observes a frequency that is higher than 2 disturbances per second, and the observer away from whom the bug is moving observes a frequency that is less than 2 disturbances per second. This effect is known as the Doppler effect. So, what is the Doppler effect? The Doppler effect is observed whenever the source of waves is moving with respect to an observer. The Doppler effect can be described as the effect produced by a moving source of waves in which there's an apparent upward shift in frequency for observers toward whom the source is approaching, and an apparent downward shift in frequency for observers from whom the source is receding. So, if the source is moving toward an observer, the frequency or the pitch gets higher for the observer. If it's the other way around and the source is moving away from the observer, that means the observer will observe a lower pitch or a lower frequency. It is important to note that the effect does not result because of an actual change in frequency of the source. Using the example from before, the bug is still producing disturbances at a rate of 2 per second. It just appears to the observer whom the bug is approaching that the disturbances are being produced at a frequency greater than 2 disturbances per second. The effect is only observed because the distance between observer B and the bug is decreasing and the distance between observer A and the bug is increasing. The Doppler effect can be observed for any type of wave: water wave, sound wave, light wave, etc. We are most familiar with the Doppler effect because of our experiences with sound waves. Perhaps you recall an instance in which a police car or an emergency vehicle was traveling toward you on the highway. As the car approached with its siren blasting, the pitch of the siren sound, a measure of the siren's frequency, was high. Then, suddenly after the car passed by, the pitch of the siren sounded low. That was the Doppler effect, an apparent shift in frequency for a sound wave produced by a moving source. If you want to know something really cool about the Doppler effect, it's actually used very often in astronomy. That's right, astronomy. The Doppler effect is of intense interest to astronomers who use the information about the shift in frequency of electromagnetic waves produced by moving stars in our galaxy and beyond in order to derive information about those stars and galaxies. The belief that the universe is expanding is actually based in part upon observations of electromagnetic waves emitted by stars in distant galaxies. Furthermore, specific information about stars within galaxies can be determined by application of the Doppler effect. Galaxies are clusters of stars that typically rotate about some center of mass point, just like we rotate about the sun. Electromagnetic radiation emitted by such stars in a distant galaxy would appear to be shifted downward in frequency, which is called a redshift, if the star is rotating in its cluster in a direction that's away from the Earth. On the other hand, there's an upward shift in frequency, a blue shift, of such observed radiation if the star is rotating in a direction that is toward the Earth. Well, I hope you guys enjoyed watching and hopefully you learned something about the Doppler effect. Well, thanks for watching!